probability distribution is a description of what the likelihood is that some random variable will take on a particular value. So let's remind ourselves of something about probabilities. When you're looking at something and trying to decide how likely it is to happen, what are the extreme values you can have? What's the biggest and what's the smallest value you can have in terms of our probability? What are those two numbers that, yes, Marquise?
The smallest value is 0 and the largest is 1.
Good. So probabilities have to be between 0 and 1. And when you have a table that describes all the possible probabilities for all the possible, or not the possible probabilities, all the possible values and their corresponding probabilities, that table is called a probability distribution. Now there's something that has to happen about that probability distribution. When you perform this experiment, one of these values will occur. What's the probability that something will occur? It's guaranteed to occur. 100% or a 1. So this probability, this thing should total up to 1. Now, if it doesn't, if it's like 1.001 or 0.999, there's probably a rounding error. That's not the kind of question I'm going to try and trick you with on an exam that, oh, it totals up to 0.999. And I'll ask them, is this a probability distribution? And you'll say no, because it totals up the wrong way. Now, I'd make it very obvious. It total up to something like 0.8, so that it's clear it's not a rounding error that you're getting there. But how do you find the expected value for something like this? How do you find the expected value? What do you expect on average from a probability distribution? Let's tackle that with our dice example down here. So, unfortunately, I don't have two 6-sided die, but you can imagine rolling a pair of dice, and you have die 1 and die 2. These are all the possible outcomes. This is something called your sample space. It's the set of all the things that can occur. How many things are there in my sample space here? How many different possible combinations or events are there? 36. And if I wanted to, for instance, figure out the probability of a 4, since all these events are equally likely, the probability of a 4 is 3 out of 36. How about the probability of an 8? What's the probability of an 8? How many? Yeah, 5 out of 36. There's 5 ways that the dice can total up to an 8 out of the 36 possibilities, so probability of an 8 is 5 out of 36. And so on. You can keep on doing this all the way down. What do you think would happen if I added up this column here? What do you think I'll get? Well, yeah, 36 out of 36, which is 1. Now these are just the decimal values of those things. I put those in so that Excel could work with this. But there you go. If I wanted to figure out, well, on average, what do I get when I roll a pair of dice? Kind of like what we were doing with our little simulation here. With our simulation, we rolled a die, tons of times, a couple thousand times, and we found that the average roll was a little bit more than 3.5. Now, this is doing something empirically, that is by experiment. If you wanted a more exact answer for this experiment, we can do something what we're going to do here. So we're going to calculate something called the expected value. So the expected value is interchangeable with, it's a synonym for the mean, and we had a symbol for that. Do you remember our symbol that I used back in section 2.6? What symbol did I use? It was a Greek letter for the mean. It's also used, you can use that Greek letter in Words with Friends. A seal's given it to us. It's the Greek letter mu. Now my mu might not be all that legible, so let me type it in on Google. Greek letter mu. Mu. So there you go. There's your lowercase mu right there. That's the one that we're going to use. So if you want a good look at it, there it is. But all these things are interchangeable. Now to calculate the Greek letter mu, you've got to do a couple things. We've got to start with our variable x and multiply x times p of x. P of x, of course, is your probability. I'm doing that here as a decimal. X times p of x, that's in this column here. Now, the mean is the total of all these things. So mu is going to be the sum of x times p of x. And that's just notation for the sum. It's the Greek letter sigma. Now, I don't know if you've got this link open or not. If you do, you can make your own copy on D2L. You want to click example C, the tab down there. When you total this all up, x times p of x is a 7. So that's the mean, that's the expected value. When you roll a pair of dice again and again and again and again, on average, you're going to get about a 7. Now let's think about it. This is for rolling a pair of dice. We got a 7. What do you think rolling one die would give us on average? If 2 dice gives us 7, what's one die going to give us? About, go ahead, 3.5. And if you look back at our experiment, we were pretty close to that. All right, we got, what, 3.526? That's not too bad. Here's a little kind of quick reminder. Let's regard the 3.526 as the new value, and 3.5 is the old value. Let's calculate the percent change. So a relative change. Remember, it's going to be the new minus the old divided by the old, and then you can times by 100% if you want to change it to a percent. So for us, that's going to be 3.526 minus 3.5 divided by 3.5, then times 100. This is a good question to expect to be able to do for the quiz, to calculate the relative change. So let's use it to see how good our guess was. Now I'm going to exit this program here. Let's see. I can do that with the escape key again. You want to clear this? Yeah. Okay. No, I want to quit there. Let's see, escape. Yes. And then quit. There we go. Yes, I'm sure. Finally, lets me get out of there. I'm going to hit the alpha key, then the X key. That gives me a nice up and down fraction. 3.526 minus 3.5 divided by 3.5 times by 100. That's less than 1%. So our simulation of the expected value for rolling one dice was really good. We were within 1% of the actual true value. So good job on you guys. And what I'll do is I'll look through there. Whoever's value came closest to mine gets some goodies. So I'll give you your choice up there. But in any case, let's take a look back at our calculation. You're going to take the x times the p of x for each one of these, add it up, and that's going to be your mean or expected value. What the expected value is what would happen if you did this experiment a ton of times. If I did the same experiment with you with 2 dies that we did with 1 die, then it would allow us to figure out the expected value this way empirically. All right. Let me pause here for a second. Are you okay with what the expected value says? The expected value doesn't tell you what you're going to get on any one roll. It just tells you what's going to happen on average if you do this experiment again and again and again. But that average can be kind of interesting and useful. So let me go back to this page here. And I don't think I've got these things lined up too good for myself here, because I think this one, this next one is going to be, for example, D. Let's take a look at this one. The link on D2L, we're going to have to go to tab for example D. I'm sorry, I don't have that lined up better. So the short story on this one is you can calculate the expected value for particular bets. So this gambler is trying to decide if she wants to bet $36 or $10 that the number is a 36, or bet $10 that the number is a 0, double 0, 0, or 1 on a roulette wheel. Let me give you kind of a quick glance at a roulette wheel, just in case you're not familiar with what those look like. So, roulette wheel. You've got 38 numbers. 36 of them are the numbers 1 through 36. They're red or they're black. And then you've got a 0, and there should be a double 0. It's not the one I want. It should be a double 0. Roulette wheel, images. There we go. That's one. That's an American roulette wheel. I think the other one is something that they would use in Europe. But you've got the 36 numbers plus 0 and double 0. So, okay. Now, if you're going to play roulette, then let's see. You could have a bet that you're going to bet $10 that the number is 36. Or a different bet you place is $10 that the number is double 0, 0, or 1. So this is kind of like, in modern analog, would be like a parlay. All right. So it's not quite a perfect analog, but it's close. Now, when you bet that $10 that the wheel is going to come up with 36, your expected value is negative $1.06. Let's figure out the expected value for rolling either a double 0, a 0, or a 1. So the probability of double 0, 0, or 1, well, there's 3 ways that can happen. Out of the 38 possible ways there are to roll the numbers on a roulette wheel. What's the probability that it doesn't happen? Probability that you lose. This is the probability that you win. What's the probability that you lose? Well, there's still 38 options there. How many ways are there that you can lose? 35. So let's use these. Now, if you win, according to this, you win, where is it? $30, I think. Yeah, you win $30 if you win. And of course, you end up losing $10 if you lose. So I'm going to put those in as my variables for X. That should be already in your little D2R, your Google Sheets form here. So you got 2 possibilities. You got X, which is winning $30, or X, which is losing $10. Those are the only 2 things that can happen. The probabilities of those are here, but for purposes of Google Sheets, I wrote them as decimals. You can take a look that the total of these probabilities is 1, but if I want to figure out the expected value, I've got to take the product of these 2 things. I've got to take the product of X times P of X. That's here. I got to take the product of X times P of X again, which is here. Your expected value for this experiment is going to be the sum of those. So type in the sum of these 2 values. and the expected value here of this bet is minus 6.842. What is the minus telling me about either of these bets? Why am I getting a negative in this calculation at all? Okay. What's that? Yeah. On average, you expect to lose money. And that's one of the big points I want to make about this. When you're playing this game, on average, for every $10 you bet, you're going to lose $6.84. So if you were to bet $1,000, on average, you're going to lose $684. Now, the other bet that they gave you was a chance to bet $1, and if you win $35. So you're just betting on one number. Your expected value here is negative $1.06. Which game are you going to play? Which game would you think is in your best interest? You're going to have the better chance of winning in the long run. Yeah, the game I want to play, and this is the message I really need to get across to you, is that the better game to play is the one with the higher expected value. Now in this case, both of these expected values are negative, meaning on average you're going to lose money. That's going to be the case with every casino game and every scratch off and every lottery game you play. You expect to lose money. Otherwise, they wouldn't be able to afford to run the game. It wouldn't make revenue for their state, etc. So you expect to lose. But if you had a choice of these bets, this one's the better bet because the expected value is higher. You're not losing as much on average. And that's the big point that I want to make. Let's see if we can't calculate the expected value down here. So this is the expected value for losing just one, or losing when you just play one. I forget what the bet was up top. But if you're going to bet $10 on one number, then the payout is $350 if that one number comes through. Let's see if we can't calculate the expected value. So over here, I want to do x times p of x. And then I'll copy that one down here. That one's even better, isn't it? So that's a better bet than any of these other two, and that's for just playing exactly one number. So one of the messages I have for you is that it really makes a difference, where you put your money on those tables, what games you play. Because some of the payouts are good and some of them are bad. And you want to steer yourself to the better payouts, the ones that have a better expected value from your point of view. Okay. Comments, questions? Let's take a look at, now it's tab D here, but it's example, or tab E here, but example D on your handout. Let's take a look at that next one. Colorado Pick 3 lottery game. Pay $1.29 to select a sequence of 3 digits from 0 to 9, such as 899. If you select the same sequence of 3 digits that are drawn, you win $462.42. How many different selections are possible? Well, let's take a look at that. If you're selecting a 3-digit combination here, and they have to be digits 0 through 9, how many choices do I have for that first number? You got to include the 0 as well. 10. Now, based on this, that I have 899 as one of the possibilities, you can use numbers more than once. So if I can use numbers more than once, how many choices do I have in my second digit? 10, and then 10 again. So that's going to be 10 cubed. What's 10 cubed equal to? 1,000. So there's 1,000 possible winning tickets. What's your chance of winning then? What's your probability of winning? Let's use the proper notation here. Probability of winning. You buy one ticket. What's your chance of winning?
1 in 1,000?
Yeah, you got one ticket. There's 1,000 numbers there. You got a 1 in 1,000 chance of winning. Now for this next one, we got to be a little bit careful about this. It says, if you win, you collect $462.42. But is that your profit? No. What's your profit? How would I find my profit? How much money did you make when you bet your $1.29 and you won $462.42? Cora? Yeah. $462.42 minus $1.29. Anyone bang that one out?
460.
Thank you. 461 and 13 cents. Nice. So that's your net profit. You need this number to find the expected value. So let's see if we can't find the expected value. So there's two possible things that can happen here. And let me go over those. So this is example D. X and P of X. So the X is you lose your bet, so minus $1.29, or you win your bet, in which case you win $461.13. Okay. Now we know the probability of winning, right? That's 1 over 1,000. What's the probability of losing going to be then? What's your probability of losing? If you've got a 1 in 1,000 chance of winning, the rest of it's losing, right? What's your probability of losing? Yeah, 999, right? There's one winner, there's the rest of them are losers. 999 of them. 999. So that's our table. Try and fill it in. You're going to need to do two things. You need to find x times p of x, and you can do that on your calculator. And then you're going to need to add it up. And that total is going to be u. So I'll pause things here for a second. If you're watching this at home later, you can press the pause button. But see if you can't figure out the expected value for this game. Do you expect the expected value to be positive or negative? Negative, yeah. The state's not going to run this game if they're giving away money. So you expect to lose money on this bet. this one times this, and then this one times this. You've got 461.13 plus. No worries.
Forget that that's negative, so there's a negative.
Yeah, I was just making sure.
The negative is right there, so if you needed to do that, you could insert a negative.
Gotcha. Thank you.
Yeah. Okay, you need to add up the x times p of x for both of these, so that's for the first one, then you need to do x times p of x for this one.
Was it this right here?
Yeah, now you need to add those up. Okay, where's your x times p of x? This column. You need to fill those numbers in and then add them up. Did you get a negative one?
So like, is it just the same?
No, it's the sum of those two. Let me be clear about a couple things. First of all, it's the sum of these two that you have to do to get the expected value. So that's one thing. Another thing real quick here is negative signs. If you want to put in a negative sign in your calculator can do that, but don't use the subtraction sign. Your calculator will complain if you try to put in negative $1.29 this way. It's going to say that you got an error. Let's see, no, let's see, let me try it again. No, yeah, it doesn't. All right, whatever. It will oftentimes. It's doing something different there. But the negative you want to use is at the bottom row of your calculator. So negative 1.29 times 999 divided by 1,000. So let's do that. 999 divided by 1,000. And I get negative 1.28871. So let's do that here. Negative 1.28871. For the other one, that's going to be a little easier. It's going to be 461.13 times by 1 divided by 1,000, or just divided by 1,000. That's going to have the net effect of moving the decimal over 3 places to the left. So I get 0.46113. And now I just need to add up these two numbers. Now I'm feeling a little bit lazy here, so I'm just going to go up here and press the enter key. Gets that number down there. Plus, let's see if I can't do that again. Grab that one. There you go. There's the sum of my two numbers. Negative 0.827. So for every $1.29 you spend, on average, you're going to come back with 83 cents. Sounds kind of expensive after a while. I mean, yeah, your expected value is not very good, especially compared to your $1.29 investment. Oops. Times 129 divided by 1.29. Yeah, you're losing about 64% of your investment on average. Well, that's not a really great expected value. Okay. Are you able to calculate those expected values? I think we should do another one. Let's practice another one before we move on to something a little bit different. Let's see here. Let's go back to my D&D dice. And here's the one I want. Let's take a look at the 20-sided die. So there. So I can roll this for a long time, but it'd take me a really long time to figure out what the expected value is for a 20-sided die. So, let's see if we can't do it on Google Sheets. So, let's open up a new tab here on Google Sheets someplace, doesn't matter where. Let me get rid of this one. And Desmos, I can get rid of you as well. Okay, that's interesting. Now, if you got the Expectations Lab open, you might be able to open up the link here for 20-sided die. If you don't, not a big deal. That one's view only. Why is it view only? There. Now, what's the chance that I roll, say, a 5 or a 7 with my 20-sided die? What do you think the chance is that I roll a 7 with that 20-sided die? 1 out of 20. How about the chance of rolling a 2 or a 1 or a 5? Same thing, 1 out of 20. So let's list all the different possible things that can happen when I'm rolling that die. I can roll a 1 or a 2 or a 3 and a 4, etc. Now you can type all these numbers in as you want. I'm going to try and be a little bit more clever about this because I don't really feel like typing in all those numbers. So what I'll do is I'll take and type an equal sign and click this and then add 1. So it's going to take and add 1 to the number above it. And then over here I'll write 0.05, which is really 1 divided by 20. So I've got those two set up, and I'm just going to copy and drag this all the way down to 20. Okay. So there's my x and there's my p of x. If I wanted to calculate the expected value, I need to be able to take x times p of x and then add it all up. So let's put that in this column. Equals x times p of x. That'll go in that column. I'll copy it all the way down, then add it up. See if you can't match that calculation. Try and find the expected value. Raise your hand if you think you got it and you think you got it right first. So in column C, you want this one times this one, and that's it. It asks, do you want to do this all the way down? Sure, if it's giving you that suggestion, do you want me to do your work for you? You click yes. Yeah, do my work for me. Let's go all the way down to, well, I guess I got to go one more. So let's copy this down one last time. Bam.
You're missing one at one.
Yeah, I'm missing one up here. Let's copy, paste. There we go. So 10.5 is the expected roll. On average, if you played D&D an awful lot and you're rolling that 20-sided die a lot, so it's called an icosahedron, in case you're curious. Your average roll is going to be 10.5. Now, you can't roll a 10.5 with this die, but that's your average roll. So let's take a look at one last thing here. Let's go back to my handout and zoom out. The Michigan Lottery has a game called Keno. They have 80 numbers, they draw out 20, and depending on how many you play, you can try and match 4 out of the 20, or 5, or 6, or 7, all the way up to 10. And I've gone through and I've computed the expected values for each of these different ways to play Keno. Which one would you play? Which one says, yeah, that's the best one to play? Answer to yourself first, and then compare your answer with a neighbor. Do you and your neighbor agree that the best of these games to play is this one? Which of these do you think you're going to play? Which one would you choose to play if somebody says, here's 10 bucks, go play some Keno with the Michigan Lottery? Go ahead. I expect to hear some chatter, so you don't have to be really shy. Which of these games would you expect to play? And by that token, which would be the worst to play? Max, coming for you. All right. What's one thing that these expected values all have in common? They're all negative, right? Now that makes sense because the state's trying to raise money. All right. Which one's the best one? Yeah, that's the best one. Which one's the worst one? Yeah, this is the worst. And in fact, if you form a ratio between these two, the expected value of the 10 is more than 3 times the expected value or the expected loss for the 4 spot. You're going to lose your money 3 times as fast on average by playing this one as opposed to playing this one. I hope that message is coming through loud and clear. It makes a big difference where you put your money. I mean, the expected value here you're losing more than a quarter on average every time you play it. Here you're losing less than a dime, for a $1 bet. That's a huge difference. What kind of difference can that make for you? Well, let's take a look here. So I like to call this, where is it? Applied probability. And let me get over to the right page here. Lit. Last February, we went to Vegas to celebrate my daughter's 21st birthday, and I spent 45 minutes at the crap table. Now, the cool thing about the crap table is you start out with a bunch of chips, and then if you start winning, you get bigger and bigger amounts of chips. When you're all done, you push it to the box man and you say, color up, and he gives you the big chips, the hundreds. And you're like, wow. And you walk over to the cashier and you walk away with a lot of cash. Now, do I always win when I play at the casino? No. But I win more often than I lose. And it's because I understand the games I'm playing. All right, I don't make stupid bets. I know how to play it. Fortunately, Dad taught me how to play craps a long time ago, and yeah, that paid for more than a few drinks. So, yeehaw. My message, though, is if you're going to gamble, and I'm not saying you should or shouldn't, I'm just saying if you're going to gamble, you should know what you're betting. Try and understand something about the game. Take a look at the expected values if possible. And certainly you want to have the highest expected value that you can overall. Overall, what I expect from you is that you should be able to calculate expected values. So that calculation is just what we've done several times. You take x times p of x, you add up that column like we did here, add up that column, and that's going to be your expected value. There's two other names for it. What are the two other names for mu here? Expected value, I guess that's one, and the mean is the other one. That's what's going to happen on average. So again, those are things that you should know from this section. That's what I expect. Comments or thoughts on that?
You know, it's kind of funny. My mom was literally just talking about how she's going to take us to the casino for my 25th birthday.
Oh yeah? Great minds think alike. Yeah. Izzy.
What is the expected value mean in layman's terms?
So like, the expected value, let's see. This is when you're betting $1 for the game of Keno. If you're betting $1, your expected value is negative 0.09, means on average, you're going to lose 9 cents. So if you bet $1,000, on average, you'd be out about $91. Okay? It's telling you what's going to happen on average. And the fact that it's negative is telling you you're losing as opposed to winning. Let's see, where are some of the other expected values that we came up with? So let me go back to this one. Our expected value here, rolling a die, on average, you expect to get a 10.5, which sounds funny because you can't get a 10.5 with a 20-sided die, but that would be your average roll. If you added up all the rolls and divided by the number of rolls, your average would be about 10.5. We saw that when we dealt with our probability lab, our expectations lab. We had 2,286 rolls. Our average roll was about 3.5. So that's our expected value for this experiment. On average, you're going to roll a 3.5. So it's just telling you, in the long run, what do you expect? And the thing about this that, again, I'll try and emphasize, because these values are negative, in the long run, you expect to lose money. Now, do you lose money every time? No. If you did, no one would play, right? So what you want to do as a gambler is you don't want to test the waters too long. So, after a while, when I was up a fair amount of cash, I quit. I'm like, okay, I beat the odds for the short term. I know if I stay here long enough, I'm going to lose it all back. So I went home with some in my pocket, and I was very happy.
So the expected value on the money problems tells us how much you're winning or losing for every dollar you spend.
Exactly.
For every roll.
Well, it depends on, on the particular problem. Like here, we set this up, you were betting $1.29. So for every $1.29 you bet, on average, I think we lost like 80 some cents, something like that. Let me look back at my sheet here. So equals, yeah, the sum of those two. Yeah, so for every $1.29 you bet in the Colorado lottery, you'd lose about 83 cents. So it's telling you on average what happens to your bet every time you bet. All right? Any other follow-up or further questions on that? Okay. Let me just take a look at one more thing here. Yeah, so in some of your work, they're doing the exact same kind of thing, finding the role, the outcome, x times p of x, add that up, that'll tell you your expected value. All right, so definitely expected value is something I would suggest you're ready for on the quiz this Thursday.